हेलो दोस्तों, मैं हूं आपका ऋषि सर और आज हम डाइव करने वाले हैं साइंस के एक सुपर इंटरेस्टिंग चैप्टर में, चैप्टर 12, मैग्नेटिक इफेक्ट्स ऑफ इलेक्ट्रिक करंट। रेडी हो?
So, we all know that electricity, it powers our lights, our fans, our homes. But have you ever stopped to think that maybe it has some secret powers? That it can create these invisible forces that can actually make things move? Well, chalo, let's solve this mystery together. To understand this whole mystery, let's start with something we've all played with as kids, magnets. You know that invisible area of force around them? The one that lets them attract or push away other things? That, my friends, is what we call a magnetic field. But how do you see something that's invisible? Well, scientists came up with a clever idea. They use something called magnetic field lines. Just think of them as imaginary pathways that show us which way a tiny little north pole would travel if we placed it inside that field. Simple, henna? Now, these field lines aren't just random scribbles. Nope. They follow some very important rules that you absolutely have to remember. First, they always form continuous closed loops. Second, they start from the North Pole and go into the South Pole. That's outside the magnet. Third, wherever the lines are crowded together, that's where the field is the strongest. And the most important one, star mark this for your exams. No two field lines can ever cross each other. Never. But why can't they cross? Well, just think about it. If you're at a crossroads with two different paths, a compass would get totally confused, right? A single compass needle can't point in two directions at the same time. It's just like a line at a temple, dolstan. Everyone follows the person in front. No one cuts across. It's that simple. Okay, so far we've only talked about magnets, but the chapter is called Magnetic Effects of Electric Current. So it's time to connect the dots. Let's uncover electricity's big secret. So here it is, the biggest secret of this entire chapter. Listen very carefully. Whenever an electric current flows through a wire, it creates a magnetic field all around it. This was an amazing discovery by Ørsted, and it proved that electricity and magnetism are like twin brothers. All right, so a magnetic field is created. We get it. But what's its direction? Is it up, down, left, right? Well, for this, we have a superhero tool. It's called the right-hand thumb rule. Come on, do this with me right now. Everybody, put your right hand up. Very good. Now imagine you're holding the wire. Point your thumb in the same direction the current is flowing. Now look at your fingers. The direction they are curling in, that's the direction of the magnetic field. See? How easy was that? It's like giving a thumbs up to physics. Okay, now let's get creative. What if we take that straight wire and bend it into a circle, a loop? Well, what happens is that inside the loop, all the magnetic field lines get concentrated, all pointing in the same direction. And what does that mean? It means a much stronger magnetic field. There's strength in unity, right? Now let's take this idea one step further. What if we don't just have one loop, but lots and lots of loops, all wrapped together tightly, just like the spring inside your pen? Well, this cool structure has a name. We call it a solenoid. And here's where the magic happens. When you pass a current through the solenoid, its magnetic field looks exactly like the field of a regular bar magnet. One end becomes the North Pole, and the other becomes the South Pole. We've basically just created a magnet using electricity. Isn't that amazing? And what if we put a piece of soft iron inside that solenoid? Boom, we get an electromagnet. This is a temporary magnet that only works as long as the current is on. You switch the current off, the magnetism vanishes. It's super powerful, and it's used in things like giant cranes and even your doorbell. So we've made magnetism from current. That's cool. But what's the point? Can we actually do something useful with it? The answer is yes. We can create motion. Cello, let's see how we go from magnetism to force. This whole idea came from the great scientist André-Marie Ampère. He suggested that if a current-carrying wire can put a force on a magnet, then according to Newton's third law, the magnet should also push back on the wire with an equal and opposite force. And he was absolutely right. To prove this, there's a really simple experiment in your textbook, Activity 12.7. I like to call it the kicking wire experiment. All you do is take a small aluminum rod, hang it so it can swing freely, and place a powerful horseshoe magnet around it. And then you see the real magic. The moment you pass a current through that rod, it moves. It actually gets a kick to the side. This is the proof we needed. It shows that a magnetic field exerts a real force on a wire with current. And this is the basic principle behind every single electric motor in the world. Now, a question for you. Let's think about this for a second. What do you think would happen to that force, to that kick, if we increase the current flowing through the rod? Would the force get stronger or weaker? Zyada force लगेगा या कम? Think about it and let me know your answer down in the comments. I'll be reading them.
So we know a force will be there. But in which direction? Will the wire kick up, down, to the side? For this, we need the final superhero tool of this chapter. Let's master the direction rules.
And this tool is called Fleming's left-hand rule. We use this rule to find the direction of the force, or in other words, the motion. This one is super, super important for understanding how electric motors work.
Okay, now everybody, use your left hand. Listen to me carefully on this, no mistakes. Stretch out your thumb, your forefinger, and your middle finger so they're all at right angles to each other. Now just remember this. Forefinger is for the field, middle finger is for the current, and your thumb shows the thrust, or the force. So you point your forefinger in the direction of the field, put your middle finger in the direction of the current, and your thumb will automatically point in the direction of the force. Simple.
So this very rule is what makes all electric motors spin. Now here's your second question. Can you name just one device in your house that you think uses an electric motor? Have a look around, think about it, and tell me in the comments. All right, let's quickly summarize everything we learned today. First, an electric current always produces a magnetic field. Second, a magnetic field puts a force on a wire that's carrying current. Third, to find the direction of the magnetic field, you use your right-hand thumb rule. And fourth, to find the direction of the force, you use Fleming's left-hand rule. You remember these 4 points, and you've mastered this chapter.
And that's it for today, champions. I really hope you understood everything well. If you have any doubts, just watch this again. Keep revising and always keep asking questions. Padhte raho, badhte raho. See you in the next one.